Hello, everyone. Welcome back to my CellRank video tutorials. In previous video, we estimated the cell fit probabilities. So in this video, we continue our analysis to identify the driver genes for cell type differentiation. So first we can use beta cell as an example to perform the analysis. So let's have a look at how the CellRank defined the driver genes. So if a gene has systematically higher expression in cells that are more likely to differentiate towards a given terminal state, for example, beta cells, then this gene will be defined as a putative driver gene. Because we are going to use the beta cell differentiation as an example, so first we can set the driver canisters. In the pancreas, we start from the NGN3 low expression, then high expression, then FEV positive cells to beta cells. This is the trajectory for beta cell differentiation. So we set the driver canisters first. Now we can use the function computer lineage drivers to uncover putative driver genes by correlating the fit probabilities with gene expression in the cell canisters that we set up here. So in the argument, we set the lineages as beta cells. If you are interested in other cell types, you can set as other cell types. Later, we are also going to get the driver genes for alpha cells. Then the canisters will be driver canisters we set up already here. Then canist K will be the canisters to label all the cell types in this data set. So let's compute the lineage drivers to get a data frame for beta cells. At the same time, we can have a look at the first 10 genes. Let's perform the analysis. So you can see it is very quick. We generated the data frame for beta cells. You can see here, it shows the top 10 genes that are highly expressed in beta cells. They are ranked by the beta cell correlation. You can see the gene names here, the NNET, insulin 2. So we know they are highly expressed in the beta cells. Then here is the p-value and the q-value. So we identified the driver genes for beta cell differentiation. The way they named the genes as the driver genes, which means actually high expression in the terminal cell state. Normally we consider the transcription factors as the driver genes. So now we can realize the putative driver genes on the UMAP. We can set the counter argument as top 6 genes we identified here and make the UMAP to see the gene expression in different cell canisters. Let's make the UMAP. You can see we generated 6 UMAP for the top 6 genes show high correlation in beta cells. You can see from the expression they are highly expressed in the beta cell canisters. So we use the beta cells as an example. Next, we can identify the driver genes in the alpha cells. Now we can set the driver canisters from NGN3 low to high, then FEV positive to alpha cells. If we use the computer lineage drivers function, the canisters argument will be the alpha driver canisters we set up here. Now we can run the analysis and show the top 10 driver genes for alpha cells. You can see we identify the highly expressed genes in alpha cells. Then here we show the top 10 genes. You can see they are ranked by the alpha correlations. The first one is the glucagon. We always use this gene as a mark gene to identify alpha cells. So glucagon is the top one driver genes for alpha cells, but we know the glucagon is secreted by alpha cells to regulate glucose metabolism. It prevents the blood sugar level drop to very low level. Again, I don't think the glucagon is a driver gene for alpha cell differentiation. So here we identify the highly expressed genes in alpha cell lineage. So I showed you how to identify high correlation genes for terminal cell stage. We performed the analysis for beta cell and alpha cell. When we perform the analysis, here we set the lineage as beta cell or alpha cell. If we run the same function but leave the arguments blank here, we will get the driver genes for all the terminal cell states. Let's run to make a data frame and name it as driver data frame. Then we can have a look at the first 10 genes. We can run it. Now you can see in this data frame, we have the alpha correlation, beta correlation, epsilon correlation. If we move to the end of the data frame, you can also see the delta correlation, which means if we run this function with the argument blank, we will get driver genes for all the cell clusters in terminal states. Because we got the driver genes for all the terminal state cell clusters, now we can realize top correlating genes for selected lineages using the function plot lineage driver correlation. For example, here we are going to plot the lineage drivers correlation between alpha cells and beta cells. So here you need to set the lineage X as the first cell type and the lineage Y as the second cell type. Then we can make the plot. Let's make this plot first. You can see the x-axis is the alpha correlation and the y-axis is beta correlation. We have genes are positive for beta correlation and genes in this area they are positive for alpha correlation. Because this image is black and white, we can make it more beautiful. For example, we can define a set of genes to annotate the genes on the plot. You can manually define the mark genes for different cell types, or you can select transcription factors. They are real drivers for cell differentiation. For demonstration, we are going to get the top 10 genes that we identified above for alpha cells and beta cells. We can just get the gene names from the data frame. We know they are ranked by linear correlation. So we can get top 10 genes for alpha cells and top 10 genes for beta cells and set them as the gene of interest for annotation. We can do this now. You can see in this plot, the gray dot represents the gene. So all the genes are in gray color. We can color the genes by their average expression in this dataset. So we need to get the mean expression for each gene from the dataset. Let's run. Now we can make the plot again. So here you can see we set up two more arguments. We will count the genes by mean expression, then annotate the gene names with top 10 genes for alpha cells and the top 10 gene for beta cells. So let's run the plot again. You can see we generated a plot now. It is more colorful now. You can see the y-axis is beta correlation, x-axis is the alpha correlation. We counted the genes with their average expression in this dataset. And also, we labeled the top 10 genes for beta cells and the top 10 genes for alpha cells. You can see the top 1 correlation gene for alpha cells. Can look again. So I just use beta cells and alpha cells as the example. You can plot other cell types in this dataset. Or if you are analyzing your own dataset, you can set the cell types that you are studying in your research project. Okay, that's today's demonstration for identify the driver genes. In my next video tutorial, I'm going to show you how to perform the analysis to realize and cluster the gene expression trends. I hope to see you in my next video tutorial.